Hi, Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon, everyone. We have finished our chapter 4, chemical bonding. We have covered 4.1, 4.2, 4.3, 4.4, and 4.5. So today we are going to enter a new chapter, which is chapter 5, which is states of matter. And today we are going to focus on chapter 5.1 gas. So in this chapter gas, we are going to explain qualitatively the basic assumptions of the kinetic molecular theory for an ideal gas. Next, we are going to define the Boyle's, Charles, and the Avogadro's law. We are going to also sketch and interpret the graphs of Boyle's and Charles' law. And we are going to perform calculations involving gas laws and ideal gas equation. And lastly, we are going to determine the molar mass of a volatile liquid using ideal gas equation. So these are the learning outcomes that we are going to fulfill for today's tutorial class. Alright, so first, let's see what is kinetic molecular theory of gases. Okay, so it says that the gas that follows this theory is an ideal gas. So it says that a gas that behaves according to kinetic molecular theory is known as ideal gas. So ideal gas is equals to the perfect gas. Okay, so there are a few basic assumptions of kinetic molecular theory of gases. So the first one is it is assumed that the volume of gas molecule is negligible. Since the size of the gas particles is too much small than the volume of the container, the space of the container, the gas particles actually is located separately, very much far apart from each other. It has a great distance, and there is a lot of empty spaces in between them. So since that is the case, so we assume that the volume of gas is rather negligible. It's not really significant in this case. Alright, and the second one, it says that the collision among gas molecules are elastic. Okay, so gas particles move in a random and continuous motion. It continuously collide with each other. So what does it mean by the collision is elastic? So that means that the kinetic energy before the collision is equal to the kinetic energy after the collision. There is no loss in kinetic energy when the gas particles collide with each other. Alright, and the third one is the intermolecular forces between gas molecules is negligible. So there is no attraction or repulsion between the gas particles since they are so far apart from each other. So they just collide, and that's it. Alright, and lastly, the average kinetic energy of molecules is proportional to the temperature of gas. So when the temperature of gas increases, hence the kinetic energy of the gas molecules increases. This is directly proportional. Alright, so if the gas behaves ideally, it will follow this kinetic molecular theory of gases, this assumption. Okay, alright, next we're going to move on to the gas laws. So what is gas laws? So gas law actually describe the changes in the physical properties of gases under specific condition. Alright, so there are three gas laws that we're going to learn in this chapter. So the first one is Boyle's law. Alright, Boyle's law. Oops. And the second one is Charles' law, and the third one is Avogadro's law. So let's see what is Boyle's law. So Boyle's law it explains the relationship between the volume of gas and its pressure. Alright, we are going to look up into more detail after this. Alright, next, Charles' law, it explains the relationship between the temperature and the volume of gas. And lastly, Avogadro's law explains the relationship between the volume of gas and its amount. Alright? So we are going to look at each of these gas law. So first, let's look at what is Boyle's law. So Boyle's law states that for a fixed amount of gas at constant temperature, the volume of gas is inversely proportional to the pressure of a gas. Inversely proportional. So that means when the volume of gas increases, the pressure decreases. It's inversely proportional. Berlawanan. Okay, so now let's look at this picture and its explanation. Alright, look at the first picture. It has larger volume with a lower pressure. Lower pressure. So when there is a large space inside the container and lower pressure exerted on it, there will be fewer collisions per unit volume. However, when there is a high pressure with a small volume of a container, there will be more collisions between the gas particle per unit volume. So in this explanation, we can see that when the gas volume decreases, okay, when the gas volume decreases here, look at the second picture, the gas molecules are drawn closer together. So the gas particle will be moving towards each other more closer and exert more collision. So when the space is small, they tend to collide each other more often. Okay, more collision will happen between the gas particles. Thus, the pressure of gas increases. Yalah, when the space is small, then the gas particle collide with each other more frequently. So lagi banyak pressure, high pressure. So the smaller the volume, the higher the pressure. The bigger the volume, the lower the pressure. Okay? Alright, so let's look at the mathematical formula for Boyle's law. So it says that at constant mass or at constant amount of gas and temperature, the volume is inversely proportional to the pressure. And if we change this proportionality constant jadi macam equal sign, we can get PV equals to K constant. Alright? Okay. So PV is equals to K. So at different pressure and volume, we can say that P1V1 is equals to P2V2, where P1 is the initial pressure and V1 is the initial volume, P2 is the final pressure and V2 is the final volume. So we are going to use this equation or this formula when we have two different conditions. Like for example, like they give you the initial pressure and volume, they want you to find the final pressure when the volume is certain amount. Okay, so this is when we use this formula. Okay, all right. Next, we are going to look at the graphs. So there are three graphs in this what we call this law, in this Boyle's law. First, we look at this graph. Okay, the first graph is V against pressure, where we know that volume of gas is inversely proportional to the gas pressure. So this is the graph. This is the line for the graph. When it is inversely proportional, dia macam lengkung macam tu. It's like a white lengkung lah. Alright. Okay, next, the second graph is when gas volume is directly proportional to the 1 over pressure. So like we know from the formula, this one, V is directly proportional to 1 over P. So that's why graph is line yang tegak tu. Alright, so V is directly proportional to 1 over P. It's like this, okay, the straight line graph. Alright, next we got the graph of PV against P or against volume. So since we know that PV is equals to K constant, so this is the graph for it. So PV is constant. That means since PV is a constant, is a constant, hence PV is actually independent of P or V. So this is why the graph is like this. Okay? Alright. It's very simple. Okay. Now we're going to move on to the next gas law, which is Charles' law. So just now for Boyle's law, the temperature is constant. So the volume is inversely proportional to the pressure. Okay, so for Charles' law, the pressure is constant and the volume is directly proportional to the temperature. So let's look at the definition. So for the full definition, Charles' law states that for a fixed amount of gas at constant pressure, the volume of gas is directly proportional to its absolute temperature in Kelvin. Okay, so dekat sini constant N P. Tadi constant dia and N dengan temperature. Now constant dia adalah number of mole and pressure. So this is what Charles' law means. So let's look at the definition for the explanation for this Charles' law. Okay. Look at this. Both of the container has the same pressure. This container one has the pressure of 1 atm. This second container has the pressure of also 1 atm. So what's the difference? So we look at the volume and the temperature here. So the temperature for the first container is 300 Kelvin, while the temperature for the second container is 600 Kelvin. So we know that V is directly proportional to T. So when the temperature increase, the volume of the gas increase. So let's look at the explanation. It says that here, the kinetic energy of a gas molecule increases when the temperature increases. So kinetic energy increases. Yeah. When the temperature increases, the gas molecule tend to move faster. That's what we call kinetic energy lah. The tendency for the gas particles to move even faster lah. So when the kinetic energy of the gas molecules increases, So when the temperature increases, the kinetic energy of the gas molecules also increases. So the number of collision with the wall of container also increases, which in turn increase the pressure actually. However, here we know that, in order to keep the pressure constant, the volume of gas increases. So disebabkan asalnya volume dia macam ni je, alright? This is the volume, kecil je volume dia. Okay, but when we increase the temperature, okay, when we increase the temperature, we know that the kinetic energy will increase, so the collision will increase, it will increase the pressure. So what we do, we increase the volume of the container so that the pressure will remain 1 atm. Okay, so that's why. Alright, so this is the explanation for it lah, for the Charles law. Okay. Alright, I hope that you can grasp the concept of this Charles law. Okay, so alright, so let's look at the mathematical formula. So it says that at constant mass and pressure, the volume is directly proportional to its absolute temperature in Kelvin, and when V over T is equals to K constant. When we convert this into proportionality constant, we convert it into K. So this sign will be equal lah. Okay. So at different temperature. So when there is different temperature where we want to find the final and initial volume, for example, we use this formula V1 over T1 is equals to V2 over T2. Okay? Alright. Now let's look at the graphs here. So there are two graphs for this law, for this Charles law. First is the volume against temperature in Kelvin. So the gas volume is said to be directly proportional to the absolute temperature in Kelvin. Okay, so there is straight line lah. Okay. Next, the second graph is extrapolate punya graph. Okay, where the graph is between volume against the temperature but in degrees Celsius. So in this case, on extrapolation, the graph meets the temperature at negative 273.15 degrees Celsius. So this temperature is called absolute zero. Okay. So this temperature is called absolute zero in Kelvin scale. So we know that to find the temperature in Kelvin, we need to plus with 273.15. So we know that negative 273.15 degrees Celsius is actually equals to 0 Kelvin. Okay, so this is the absolute zero punya graph lah. If the question asks you to sketch the extrapolate punya graph and what we call it, label the absolute zero temperature, so this is what you do lah. Alright, so that is all about Charles' law. So now we are going to move on to the last gas law, which is Avogadro's law. So in Avogadro's law, it states that at constant pressure and temperature, so dekat sini constant dia adalah pressure and temperature. So at constant pressure and temperature, the volume of gas is directly proportional to the number of moles of the gas present or to the amount of the gas present. So number of moles ni biasanya we kaitkan dengan amount of gas. Okay. So explanation dia. So gases with equal volume, so any gases that have the same volume will contain the same number of mole at the constant temperature and pressure, regardless their chemical properties. So this is what Avogadro's law states. Okay. So for the mathematical formula, we know that at constant pressure and temperature, the volume is directly proportional to N. So V over N is equals to K, constant. And note here that usually the question regarding this Avogadro's law will ask you to find the volume of gas at STP at the room temperature. So know that the volume of gas at STP is 22.4 decimeter cube or liter, and the volume of gas at room temperature is 24 decimeter cube or 24 liter. Okay, and there are a few conditions when we want to find the volume of gas at STP. First, the condition is the pressure must be 1 atm and the temperature must be 0 Kelvin. 0 Kelvin pula. 0 degree Celsius. I'm sorry. 0 degree Celsius or 273 Kelvin. These are the condition untuk gas at STP. Alright, so we are going to look at this question in the tutorial book later on. Okay, so don't worry, we are going to look at that. Okay. Now, we are going to look at the combined gas law. So this is what I got from the lecture notes. So the combined gas law is basically the simple combination of Boyle's law and the Charles laws. For example, we know that for Boyle's law, V is inversely proportional with pressure, and for Charles' law, V is directly proportional to T. So when we combine this, we got V is directly proportional to T and inversely proportional to V, and N is fixed. And we got PV over T is equals to constant, and at different condition we can use this equation. P1 V1 over T1 is equals to P2 V2 over T2. It's very simple. Okay, what we're going to look at now is the ideal gas equation. So we want to know what is ideal gas actually mean. So ideal gas is actually a gas that obeys all the gas law. It obeys the Charles law, it obeys the Boyle's law, it obeys the Avogadro's law. It's a perfect gas. It obeys all the gas law. Okay, so here, having said that, we know that the ideal gas equation then will actually describe how the volume of gas is affected by the changes in pressure, in temperature, and number of moles. And we can derive this ideal gas equation from all the gases laws that we have learned just now. So we can see that the Charles law, V is directly proportional to T, Boyle's law, V is inversely proportional to pressure, and Avogadro's law, V is directly proportional to N. When we combine all this formula, we get V is directly proportional to NT over P, where when we convert this proportionality constant into gas constant, we get PV is equals to nRT. So R is the gas constant, and temperature must be in Kelvin. Okay, and there are a few value of R that you need to pay attention on it lah. First, there are this one 0.08206. So this is the most common one lah that we use. Either this one or this one or this one. Okay, we usually use this one lah. Okay, these three lah. Okay, memang guna semua lah, senang cerita. Okay, so how you want to know which values of gas constant that we can use? We can look at the pressure punya unit, whether they use Pascal, kilopascal, mmHg, atm ke, look at that one lah. Okay, look at that to identify whether you want to use this value of R or this value of R or this one near R. Okay, so now we want to look at the relationship between the ideal gas equation with the mass, molar mass, and the density of gas. So we know that PV is equals to nRT. And we know that the number of mole is actually equal to mass over molar mass. So having said that, when we substitute the mass over molar mass into the equation, into the formula, N, we get PV is equals to mass RT over molar mass. When we arrange the equation and change the molar mass as a subject, we get molar mass is equals to mass RT over PV. Okay, we also know that the density is actually equals to mass over volume. So since we get this mass over volume here, we can substitute this density into the formula. So when we substitute, we get molar mass is equals to density RT over pressure. Alright, when we arrange the equation, arrange the formula, we get density is actually equals to pressure molar mass over RT. So this is how we actually derive and relate the ideal gas equation with the mass, with molar mass, and with density of the gas. Alright, so I really hope that you guys can understand this chapter, because this is only half of chapter 5.1. We are going to continue the rest of the chapter tomorrow. Okay, maybe tomorrow. Yeah. Okay, so we have learned about kinetic molecular theory of gas. We know that there are three gas laws, which are Boyle's law, Charles' law, and Avogadro's law. We already know what is the definition for all these three laws, and we already know the mathematical formula for all these three laws. We all know how to do the graph for this law, and we know that the combination of the three gases law will produce ideal gas equation, and we know that this ideal gas equation can be derived to explain the relationship between the mass, molar mass, and the density. Okay, now we are going to answer a few tutorial questions in your tutorial book. Okay, if we look at your tutorial book, okay, for question 1 in your tutorial book, it asks you to state the Boyle's law, Charles' law, and Avogadro's law. Oh my god, this definition is already inside your notes and even inside my whiteboard punya notes. So you just have to copy and paste. Okay, copy and paste. All right. So I would encourage you to write the definition in words and also in the formula. And don't forget to state what is the constant for each of the gas law. Okay, let's look at question 1b. It asks you to sketch the graph of V against T at fixed pressure and V against P. This one is also inside the notes and also inside my whiteboard notes that I will be giving to you after this. Alright, next look at question 2. 2a, it asks you to derive the ideal gas equation PV equals to nRT from the ideal gas law. So I have already stated, I baru je ajar tadi how you can combine all the gases law into ideal gas equation. And B, using PV equals to nRT, derive the mathematical formula which connect density of gas and gas pressure. This one is also here. This is the answer, dah ada dah, right? So it's very simple. So what we are going to do is we are going to answer the question 2C. Okay. Okay, let's look at the question 2C. It says here that the density of noble gas is 2.71 gram per liter at 0 degrees Celsius and 3 atm. Identify the noble gas. So we want to find the molar mass lah. When we find the molar mass, then we can identify the noble gas from the periodic table. So when we know the molar mass, we can find it inside the periodic table. Which noble gas is it, right? Okay. So now, first, we know that when we derive the equation, we know that the density is equals to pressure molar mass over RT. When we arrange the formula, we know that the molar mass is equals to density RT divided by pressure. So we just substitute all the information given. So 2.17 gram per liter times R. Which R we want to use? This is ATM, so we want to use the 0. What happened? 0.08206 liter ATM per mole per Kelvin times temperature 0 degrees Celsius is equal to 273 Kelvin over pressure 3 atm. Oops. What happened here? Something wrong with this. Okay. It's okay, we just do it again. Over 3 atm. Kan? We just substitute. We just put in all the information given into the formula. Density RT over atm. So when we calculate, we will get 20.23. Okay, how we want to know the unit? Okay, atm cancel. Kelvin per Kelvin dengan Kelvin cancel. And then per liter and liter cancel. So we got gram per mole. So 20.23 gram per mole. Okay, when we look at the periodic table here, we find we set for 20.23. Mana yang dekat-dekat dengan 20.23? So it's neon gas. So from the periodic table, the noble gas is actually neon. So this is the answer for this question 2C. Okay. Now, let's look at question number 3. So question number 3 is a bit tough. Okay, it's a bit, you need more understanding on this chapter. Okay, now let's look at question 3. It says that here, when an evacuated glass vessel weighing 134.74 gram was filled with unknown gas Y, the pressure was found to be 99.3 K per nanometer Newton meter squared at 31 degrees Celsius, while the mass was 137.28 gram. So the glass vessel was then filled completely with water and the mass was 1067.9 gram. By using the ideal gas equation, determine the relative molecular mass of gas Y. Okay, so this is the mass of the vessel, this is the mass of the vessel plus the gas Y. And this is the mass of water plus vessel plus Y. Okay. So first we need to find the mass of gas Y first. So the mass of gas Y is 137.28 minus 134.74. So that means we get 2 we got 2.54 gram of gas Y. So now we want to find the mass of water. Okay, here I put 1067.9 minus 134.74. Okay, the question is, why did I minus this with 134.74 instead of 137.28? Okay, we know that gas is very small. Okay, the volume is too small, the mass is too small. Once we fill the big vessel with water, the mass of the gas Y is not significant at all. It's just too small that the mass that when we put inside the water inside the vessel, we assume that all the mass minus the mass of glass vessel is the mass of water. Faham ke? Since because gas tu dia actually too small and it actually fill up the space inside the glass vessel. So according to the kinetic molecular theory of gas, we can assume that the volume of gas is negligible. Okay. Here, the mass is also very small compared to the total value, total amount or total volume of the vessel now, 1067 is very small. So we consider it negligible. So that is why when we put water, we just minus from the so we just use that the total mass minus the mass of the vessel. No need to include the mass of gas Y. So when we do that, 1067.9 minus 134.74, we got 933.16. Okay, 933.16 gram. Okay. Remember, in this case, once we fill in the water, then we consider the mass and the volume and everything negligible. So that's why we minus 1067.9 minus the initial mass of vessel tadi lah, 134.74. We got 93.16. Now, volume of gas is equals to volume of vessel is equal to volume of water. Okay, remember, the volume of gas is not equal to the volume of gas molecule. It's a completely different thing. Okay? Volume of gas is negligible. Volume of gas here means that the volume of container, the volume of the vessel. Since the gas is actually located, since the gas is actually fill up the space inside the vessel, so we assume that the volume of gas here is actually the volume of the container. Okay, so the volume of gas is equal to the volume of vessel and equal to the volume of water, since water fill up all the space inside the vessel. So the volume of water is equals to the mass divided by density. So density of water is 1 gram per ml. So gas here, the mass here, mass water is 933.16. So 933.16 divided by 1. So we got the volume of water is equals to 933.16 ml or 0.933 liter. Okay. So now we can find the molar mass. How? We can just substitute all the information that we have inside the formula. So mass, we know that the mass of it is, of gas Y is 2.54. So 2.54 gram R, which R we want to use? Okay, first we need to convert this first. So we need to convert 93.3 kNm into ATM. So 99.3 k Newton meter squared is equals to 0.98 ATM. You can find it inside the inside your lecture note. There ada table of conversion there. So check that out. Okay. So equals to 0.98 ATM. So R dia adalah 0.08206 liter ATM per mole per Kelvin. So we use this R since the pressure is in ATM. We already convert into ATM. So times dengan temperature. Temperature dia 31 degree Celsius plus 273 Kelvin is 304 Kelvin. Okay. Over P. Pressure tadi berapa? 0.98 atm. V tadi volume in liter 0.933 liter. So when we calculate everything, we get the molar mass. Okay. So remember to cancel this one. Liter, Kelvin dengan gram per mole. So we got 60.69 69.30 gram per mole. So the question asks you for the relative molecular mass. So you convert, you get the relative molecular mass. We cancel the what we call this unit. We get 69.30. So this is the relative molecular mass for gas Y. Okay. All right. Okay, remember this is what we call this. See, you have to relate this with the kinetic molecular theory of gases. All right. Okay. Next, we move on to the last question we are going to learn today is question 4. We are going to continue tomorrow lah untuk question lain. So let's look at question 4. 4A. it asks you to calculate the number of nitrogen atoms in a container of volume 0.5 decimeter cube at 0 degrees Celsius. The pressure of the gas is 101,000 Newton meter squared. So when we convert this, we get how many? 1 atm if I'm not mistaken. We got 0.99 atm. Okay. Alright, so first we need to find the number of mole. Okay, because we want to find the number of nitrogen atom kan, number of atoms sebab nak kali dengan Avogadro constant later on. So we need to find the number of mole. We have PV equals to nRT, and when we rearrange the equation, the formula, we get N is equals to PV over RT. So the pressure is 0.99 atm, V volume 0.5 liter. So since decimeter cube is equal to liter lah kan. Alright, so next over the R is we use 0.08206 liter atm per mole per Kelvin times dengan temperature 0 degree Celsius, so 273 Kelvin. So when we calculate this atm, liter, Kelvin, we got 0.022 mole. So we got this. So the number of mole that we got is 0.022 mole. So but the question wants you to find the number of nitrogen atom. So what we need to do is we multiply the number of mole with the Avogadro constant to find the total number of atoms. So number of mole 0.022 mole times with 6.02 times 10 to the power of 23 per mole. So we got 2.65 times 10 to the power of 22 nitrogen atom. So this is the answer for question 4A. Okay, boleh faham Next, we are going to look at question 4B. So, what is the volume of oxygen at STP? Dia nak volume of oxygen gas at STP required for the complete combustion of 2000 centimeter cube of CH4. You need to convert this into 2 liter, okay, or 2 decimeter cube. Okay. So, remember that at STP, the condition must be pressure 1 atm, temperature 0 degree Celsius or 273 Kelvin. So these are the conditions required when we want to do it at STP. So the volume of gas at STP, okay? So first you need to do the equation first. The complete equation for the combustion of oxygen with CH4. So CH4 plus oxygen, we got carbon dioxide and water. So we need to balance the equation. Next, we know that PV is equals to nRT. So we can find the number of mole. Okay, we need to find the number of mole so that we can find the number of oxygen gas reacted. Okay, so we know that N is equals to PV is equals to nRT. So N is equals to PV over RT. So P we got 1 atm. So just substitute P 1 atm. The volume is 2 liter divide okay, the R we need to use the 0.08206 liter atm per mole per Kelvin times dengan temperature 273 Kelvin. So we get the number of mole of CH4 is 0.089 mole. So now we want to know how many gas is how much oxygen gas is required to complete the combustion with CH4. So we do the stoichiometry. So from the equation, we know that 1 mole of CH4 will react with 2 mole of oxygen gas. So berapa mole of CH4 yang ada? 0.089 mole. So when we got 0.089 mole of CH4, so 0.089 will times dengan 2 will get 0.179 mole of oxygen. So we got the number of mole of oxygen already. So now we can find the volume of oxygen, right? So we know that PV is equals to nRT. When we rearrange the formula, we get volume of oxygen equals to nRT over P, where we know the N just now is 0.179 mole times R 0.08206 liter ATM per mole per Kelvin times temperature 273 Kelvin divide dengan pressure 1 ATM. When we calculate this, we will get the volume of oxygen required to complete the combustion with CH4 is 4.01 liter. Okay, so this is the answer for question number 4B. It's very simple. Okay, alright, I think we are going to stop here for now. Tomorrow, I will continue to explain question 5, 6, and 7, and I will enter the Dalton's law. I will explain about Dalton's law and answer a few questions regarding it. And then we are going to wait until your lecture finish the difference between ideal and non-ideal gas. Then we are going to finish chapter gas. So next week, I think we can move into liquid and solid. Okay, so yeah, that's it for today. Thank you for watching this video. I hope that you guys will be able to enjoy and understand this video to the fullest. And please let me know if you guys have any problem regarding this chapter, and if you still have problem about this previous chapter, you can still ask me, okay? Don't worry. I will always be there for you. Sometimes I will be late in replying your Telegram or WhatsApp, but I will reply. Just lambat atau cepat je. Okay, so that's it. We'll meet you guys in the next video. Okay, bye-bye. Assalamualaikum warahmatullahi wabarakatuh.